thank you for a very kind introduction. Today, as you all know, I am here to talk about techniques to achieve optimal implementation of an I3C target. And this presentation will cover some key techniques and best practices for achieving optimal implementation of an I3C target, which includes area, power, and performance optimization. And by the end of this presentation, you will have a better understanding of how to design and implement the I3C digital controller that meets high standard of performance and efficiency. So let's get started. Let's first take a brief look at what is MIPI I3C interface and what are the different devices that can be connected to a two-wire I3C bus. As you all know, I3C is an innovative two-wire interface by MIPI Alliance, which is the next generation chip-to-chip interconnect. And SCL and SDA are the two wires through which data and commands are exchanged between I3C devices. And the two-wire I3C interconnect dramatically enhances the speed and flexibility of legacy interfaces. That simplifies the development of innovative designs for products. And now let's talk about the bus configuration and device roles. So I3C devices can be classified into three categories based on their roles. So mainly we can have a main controller, we can have a secondary controller, and we can have target devices. And we know that the controller initiates and control the communication on the I3C bus, and it can be hosting processors, microcontrollers, or the other intelligent devices that can communicate with the other I3C devices. And target devices are the devices that can respond to the commands and requests sent by the controller device. This can be sensors, actuators, other peripherals that provide the data and perform a specific function. And we know that each of these devices play a crucial role in I3C ecosystem, enabling efficient and reliable communication between different components in a system. And although this presentation will focus on target, most of the takeaways are applicable to main as well as secondary controller. So moving on. Here, we will now explore the quirks of clock and data uses in I3C target. And through example, we will understand and practice how SDA and SCL are not exactly synonymous to data and clock in the implementation world. So here I have taken some example in which I will take some example in the upcoming slide. And we will see in some scenarios, the I3C protocol allows mutually exclusive activity on SDA and SCL lines without any mutual relationship. And to handle such scenarios, one is compelled to use SDA as a data, clock, and reset. And similarly, SCL is compelled to use as a clock, data, and reset. And at the end, there will be some clock domain crossing between these two signals. So now I will discuss some modes where SDA and SCL lines are used other than data and clock, respectively. So here I have taken a first example in which we have SCL and SDA in a start and a stop condition. So as we know in I3C, the start and stop signals are used to initiate and terminate the data transfer between two devices. The start is a signal sent by the controller to the target devices to indicate the beginning of a data transfer. And it is initiated by the controller, sending a high to low transitions from SDA line while the SCL line remains high. Similarly, on the other hand, we have a stop signal sent by the controller to target devices to indicate the end of data transfer. And it is initiated by the controller, sending a high to low transition on the SDA line while the SCL line remains high. So in both the cases, we can see that SCL is constant while SDA line is changing from high to low and low to high. It means there is no clock at the time of a start and a stop condition. So here we treat SDA as a clock. Similarly, I have taken another example of HDR restart and exit data path. And we know from the protocol, HDR exit pattern is defined as SDA starts high while SCL remains low, and SDA falls from high to low 4 times while SCL remains low for the whole time. and each SDA transition is separated by a time interval of TDIGH. That is defined by the MIPI. So and each there will be a normal I3C stop always follow the HDR exit pattern. Similarly, if I will talk about the HDR restart pattern, that is the subset of HDR exit pattern, and it is defined as HDR starts high, while SCL starts low, and SDA toggles 4 times: start high, start high to low, and fall rise, and then the next age of SCL is rising, while SDA may changes from SCL, but SCL will rise. And if I talk about the implementation part, so we when we try to implement HDR exit pattern and restart pattern, the basic model of implementation is that SCL is low here. So when SCL is low, so SCL high will reset the detector, and it only uses the falling edge of SDA. It means SDA falling edge is used as a clock, and SCL is used as a reset. And at the end, there will be clock domain crossing between these two signals. And if you want to see exact RTL implementation, that is given in the MIPI document, you can see that section SDR exit and restart pattern, and you will find this RTL implementation. And then you can see how SCL and SDA behavior is not exactly that we are expecting to behave. So third example here I have taken, that is the target reset pattern, which is used to trigger the default or configure reset action of a target devices. The target reset pattern begins with the 14 SDA transitions, while SCL is kept low, and there will be a repeated start followed by a stop, which trigger the actual reset action. So if we see here, SDA is used as a clock again, and SCL is used as a reset signal. And at the end, there will be a clock domain crossing between these two signals. So the moral of the story is same here. Just like HDR exit and restart pattern, the behavior of the SDA line is not exactly as a data, and SCA lines are not exactly at the clock. So their behavior are not exactly that we are expecting to behave. And then at the end, I have taken a snapshot of the all this discussed scenario, where we can see we know that we need to understand and taking care of implementation. Data path permutations between the clock and between these two signals must be defined as a functional constraint for proper timing closure. So here, for example, if you see the third option, where SCL rise, the transition is happening between SCL rise to SDA fall, and the timing is defined based on the TCBSR value, that is TCAS by 2. Similarly, if you see the fourth option, SDA fall, there is a transition happening between SDA fall to SCL rise, and timing will be defined based on the SCL signal for the stop. So please note that this is the only partial snapshot of all possible constraints that we need to be identified and defined properly before the synthesis. Now that we understand that the constant definitions of the primary I3C signals SD and SCL, I will talk about the implementation of a part where the implication of the constant just discussed would be appreciated. Let's talk about the digital design flow. The various milestones in digital design flow are represented in this diagram, and we know that the digital design flow refers to the process of designing and verifying the digital circuit using EDA tools. It involves a series of steps that start with the specification of the design requirements and end with the fabrication of the physical circuit. And the digital design flow is a complex and iterative process that requires the expertise in various areas such as digital design, verification, synthesis, and physical design. So here I'll be covering this green highlighted part with focus on the synthesis and the physical place and route. And the implementation objective is to reduce the gate count, timing closure, DFT coverage, and of course there will be functional sanity. And at the end, we will see how we can have a good core utilization. Now we will touch upon the synthesis of the controller, which we call design front end. And as we know that the synthesis involves translating a high level design into a gate level count, which can be used for the physical implementation. Uh, let's talk about logic synthesis. We know that the logic synthesis translates the design RTL to logic gates in a given library of technology. And the design constraints are very critical and determine the implementation efficiency. So we know that badly written constraints will result in a poor implementation with the low figure of merit. So we need to carefully define the design constraint file that will cover all the functional constraints of the design. So, for example, here, if we see the design content of the design constraint file, we have library description that will include the target library, symbol library, link library. If you see the read design part, that will elaborate and analyze the design. Now, if we talk about the most important, that is the design constraint part that defines the create generated clock, virtual clock definition, where you can set maximum maximum uncertainty, maximum latency, set input output delays. Similarly, if I talk about design exception, that is also very important, where we define multi-cycle path, false path, and disable timing, set case analysis. So the motive of this slide is focus on SD and SCL line, SCL definitions here, because we have seen in the last slides that the exact behavior of SD and SCL line are not as a data and clock. So here we need to carefully define the SD and SCL line. Since I'm talking about this synthesis optimization, so we know that the functional constraints are of course necessary to qualify the functional timing during the timing analysis and functional sign-off. We propose to simplify the constraints during synthesis by defining first define the test clock as the primary clock. Since we know that in I3C we can have a multiple clock. We can have a SDA line as a clock. We can have a SCA line as a clock. We will have a system clock. We can have a DFT clock. So take the test clock as a primary clock, and this works well because the test clock frequency is higher than the I3C target operation frequency, which is typically 12.5 megahertz. And if we consider even the HDR, DDR mode, it will work well because it will be 25 megahertz. And if your test frequency is 50 megahertz, a single clock having 50 megahertz will cover all the internal functional paths. And do the synthesis in the DFT mode. And how will you do that? There is a syntax in the synthesis in the design constraint file. You can set it as a set case analysis test mode equal to 1, and through that you can have a synthesis result in a DFT mode, and you can see how the setting a DFT clock as a primary clock, you can see your clock, your report will be greatly simplifies the internal path, and you will have we can see how it will impact our result. For that, here I am comparing the synthesis result obtained by using functional and test constraints. If we peek into the gate count of the result, the gate count of the result, we can see that in the test mode, synthesis is better than the functional mode, and we have almost 1,000 cell count reduction. And keeping in the mind that the number of sequential cell flip-flop is same in both the cases, but this is the combinational part that is the almost 1,000 cell reduction we can see in the combinational part. And this translates to area reduction as well. So we have here 35% area, which is quite significant. And since this reflects directly in the static and dynamic power consumption of the I3C target also. And along with that, if we see the less nets need to be routed, which translate to 35% connectivity reduction as well. So we can see that this would greatly help our design in physical implementation by reducing the routing congestion and achieving high core utilization. So here we can see that we have a very good result in the synthesis report if we set the primary clock as a DFT clock. Now I will talk about a physical design part, optimization, which is also known as the place and route phase. We label as the backend or place and route. This involves placing the gates and routing the interconnects on the chip using ADA tools. And here we will see that how ADA tool will play a very important role in our optimization. So we know that the MIPI I3C standard defines a time called bus turnaround time, but here we will touch upon the output delays, input to output delays, and we will see that how we can minimize our output delays, input to output delays in the design. One way is to bypass the clock tree insertion latency by isolating the final output registers from the design clock tree. And how we will do that, we will see in the next slide. And don't make output register as a part of your clock tree. This will cause a clock skew between these two registers, rest of the design, and causing reduced setup time available. But it will not impact our design because we have a very our frequency is just 12.5 megahertz, so we will have enough setup time available. So at the cost of the setup time, we can have a good input output delays, or we can say we can have an optimized input output delays. For that, here I would like to discuss how we can minimize output delay in the design. We illustrate the clock tree latency and possible bypass in the figure. The SCL drives a clock tree here, node which disperses the SCL clock in a balanced clock tree, which runs the I3C target core state machine. And this is the green part. So this green highlighted zone is the main clock tree of your design. And that will be the clock tree, which include the clock tree insertion delay in their output path. But you can have another wire that will branch out from the clock tree input side of the design that will drive the final output register. And how we will do that? For that, we can have a separate branch from there, and we can, so the blue color we can see we have a separate clock tree for the output register that will not be the part of your main clock tree. And this is because the destination registers clock one who bypassed, that will be not the part of your clock tree, can have reaches much faster than the source register clock. So since we are creating a skew in which your output register clock will be fast enough than your main clock tree. And but the only thing is that here you are compromising with your setup time available, and by keeping this you are making your hold violation very good, because at the cost of setup violation there will be very less skew between the these two paths. So this will not be consequential, because here we have enough setup margin. And for example, if our clock is 50 megahertz, we will have a 20 nanosecond setup time available. So at the cost of setup time, we can have a very good hold margin. So here we can bypass the clock tree. Since I'm talking about the keeping the main clock as your DFT clock, so here can we do something in the place and route stage also? So in this diagram, we know that there are multiple asynchronous clock domain can be possible in the I3C. For example, SDA can be a clock, SCL can be a clock, we can have a system clock, we can have a test clock. So if more than one clock domains non-synchronous exist in the design, then identify a clock source node of highest frequency Example here, clock 1, if we see, so we have a test clock, SCL, SDA, and system clock. And if we set our test mode control input as a 1, CTS will be test clock will be selected as a primary clock, and the tool will proceed with the test clock. So since we talk about the synthesis in the design in the test mode, we know that the primary clock, if we have a primary clock, test clock will be our primary clock. We extend this method in this place and route phase also, and test clock will be used as our main clock. And by doing this, the functional clock are bypassed during the clock tree synthesis. So we can have a tm equal to 1. We will set our test mode as a primary clock, and we can proceed with that. So instead of multiple asynchronous clock, we can have a single clock in our design. Here to show a clock tree distribution while designing all functional clock and their corresponding timing arc, we see that even after a clock tree balancing, we can have the maximum clock skew between two extreme cell is 380 picosecond. And this is quite enough, such as non-uniformly distributed clock skew will result in a buffer insertion for correcting the hold violation. So can we do something that we can reduce this skew between these extreme cells so that we can have a better hold margin? So for that, here we have implemented the clock tree synthesis in the test mode, and we see a much better clock tree distribution. And we see that the skew distribution, it has reduced by almost 4 times, 200 picosecond, and this would really help us in improving the figure of merit of the I3C target implementation. So if you define a single test clock as the primary clock for the clock tree definition, we would have a better balanced clock tree. And here, since we complete the implementation in the two discussed cases previously, so we can now compare a timing violation after the physical implementation. So if we try to compare the timing results of the two different nodes, we see that the internal setup timing is well met in both the cases, and it doesn't warrant any further analysis. But the internal hold timing, that is heavily violated in the first one, which is the 470 picosecond. And this violation is in the first case we have done the CTS in the functional mode, and in the second case, if you see, in which the implementation has done in the test mode, and we have a very good hold margin, very good skew, that is the it's just 8.9 picosecond. So this results in a design that will use multiple buffers to fix hold violation. So here we are saving a lot of buffers in hold violation, which translates to more power and area. So here we can say that if we have a balanced clock tree as the test clock, we can have a much lower hold timing issues, and we will continue with the hardware to fix this violation. So we will have a we need less buffer to hold the fix the hold violations. So we can see that if we set our main clock as a if we set our primary clock with the DFT clock, so DFT clock will be our primary clock. In that case, we can have a better implementation result, and here we can see that how our hold violation is almost 50 times less than the in the functional case. Now I am presenting you the final implemented I3C target digital controller in CMOS 40 nanometer technology using techniques discussed in this presentation. The core utilization is very high, that is the 96% core utilization, since we have set our clock as a scan clock. And here I have taken a demo in which we have set DFT clock as a 50 megahertz. And to conclude, by understanding the I3C design and test constants, applying them with the prudence, and one can be greatly improve the figure of merit of the implemented I3C target design. And Since many of things I talked about are applicable to I3C target, I3C controller and secondary controller as well. So these techniques are can be applied to all the I3C target devices. And here we can save a lot of power, area, and performance. We can have a better performance if we set our clock as a DFT clock as a main clock. That's the conclusion of my presentation. And I hope you found it useful. Thank you for being a patient audience.
Thank you,
Now, you, if you have
Vandana.
any question, yes.
Yes, it was interesting. Nice results on your design. We have a question. It says, do you mean by fixing the CTS in test mode, the functional mode will be fixed on the fly?
Since the functional mode has less setup requirement, because we know that the functional frequency is very low, right? It's a 12.5 megahertz. So since that it's a very low frequency, so our requirement will be also very less in terms of setup requirement. So the since we know that the DFT frequency will be much higher than the functional frequency, because here, for example, I have taken, if your DFT clock is 50 megahertz, right? That is the 4 times of your functional clock, 12.5 megahertz, right? So if your DFT clock is much higher than the functional clock, of course, in that case, you will have a very less setup time requirement, and that your design will easily pass all the setup requirements, and it will fix automatically if your DFT clock is much higher than the functional clock.
Okay. So now the question is, using the test clock for synthesis, is that based on using the set case analysis during synthesis?
Yes, so while doing the synthesis, you have an option. By default, it will take the set case analysis TM equal to 1. It means you are doing your synthesis in the functional mode. That is the general practice people do, because in most of the cases, if you see, functional frequency is much higher than the DFT clock in most of the designs. But here in the I3C, we have a special case in which our functional frequency is lower than the DFT frequency. So in that case, we can take the advantage of this, and we can set our we can set our synthesis mode, in which we can set case analysis test mode equal to 1. It means you will do your synthesis in the DFT mode, not the default mode, that is the functional mode. So you can set this syntax in your SDC file, or you can say design constant file.
Is there a certain clock frequency this needs to be run to meet the 12 nanosecond bus turnaround time and the 3 nanosecond setup time requirements? There is some clock requirements internally to meet these two timing requirements: 12 nanosecond bus turnaround
What
time
can I
and
say is, since the bus turnaround time is basically dominated by analog drivers, the digital part is very less. So we can say that reducing the output delay in digital will not be significant. So yes, here we do some techniques, but it will not impact much on your bus turnaround time, because it's mostly dominated by your analog drivers.
yeah, clear. Thank you. Also, some maybe a little more higher level question. How many gates at the end we're using for the I3C target implementation? Roughly, I mean, we don't need to give this might be company confidential, but just a rough.
Yes. So basically, if we talk about design count, it varies with the level of customization you are doing in your design. It can be anywhere between 3K to 10K. It depends on your design. What is the which type of customization you are doing in your work. So, for example, if there is no any registers, memory registers in your design, it will be very less. It will be maybe around 3K only. But if your design have a lot of customizations, for example, you have memory and it depends on your interface. So how your IP is going to interface with the SOC. So it depends on the how you it's all depends on the level of customization you are doing to your design. Again.
No, I was saying you give us a ballpark figure for the target complexity in terms of gates. Was that including like optional features like the high data rate modes, some of the high data rate modes, or was only for the standard for the SDR modes?
Yeah, so these features, of course, like all these techniques can be applicable for any features that you can have.
Mhm.
For example, it's nothing unique for the HDR DDR mode. The If you have a, like for example, feature like HDR mode, so you will have to take care of frequency as well. And since we know that the area will around 10 to 15% less if you have a HDR DDR mode, if you have not implemented. So it depends on the feature. I will not say it's a much, it's just the small part of the your feature, right? So yeah, it will increase your area by 10% or 15%.
Okay. Okay, so it's not major. Yeah, I think it's an interesting question. If there are any design consideration to keep in mind when to support the 1.2 volts operation. Was
Uh,
your design
the
already
digital
support?
implementation, I would not say, because it's not related to analog voltage, since we are talking about the RTL implementation. So I would say no as such constraints on designing, and it will be because it will be analog driver, right? Analog driver is specification, so we cannot say there will be any you need to take. Uh, precaution, or you can say you need to think about voltage while designing your core,
Mhm.
because voltage are more related to analog driver, right?
Okay. Do you consider exception like false path or a multi-cycle path during the synthesis stage?
Yes. So this is very important to consider all these paths in your design constant file. That's what I was focusing more on the this part, because once you will design, you need to take care of multi-cycle path, functional path, because once you will go for I3C implementation, you can have there are many more paths where you need to take care. For example, here I talked about three examples: target reset pattern, and SDR exit and restart pattern. So in which we have seen the behavior are not exactly. So for example, in the same design constant file, you will have to define your clock as a clock. At the same time, you will have to define your clock as a reset. At the same time, you are defining your data as a data, and at the same time you will have define your data as a clock. So you will have to take care, you will have to define it very carefully, where we can set it as a false path, where we can take a multi-cycle path. For example, there will be uh, some modes, some optional feature, like for example, there are features like you want to uh, it will be programmable only once, right? So you can set it as a false path, since you know that this will be programmable for only once. Or you can say this, if this is a static, for example, there is an input which is coming static directly, that will define your design. So you can set it as a false path as well if it is constrained by the input delays. So yes, just like a normal design, here you need to focus on the uh, definition. I would say a false path, multi-cycle path will be just like a normal design, but that you need to take care more about definition of SCL and SDA line.
Which part of the design causes maximum congestion and requires special attention?
Okay. So uh, usually the congestion will occur at the every stage of your implementation, starting from the synthesis to the place and route phase. And we know that poor constraining design will have a non-optimal synthesis result. So you will have to take care of your implement. You will have to take care of your design at every stage, so that it will not create any congestion. For example, if you will not, for example, here I have taken DFT as a your main clock, DFT clock as a main clock. So we have seen that we have a good optimization in the synthesis result, right? So if we will not do that, it will synthesize your design, but it will not be as optimized as we are doing here. So similarly, if you will not take care of your design in the CTS, so that is the very critical stage, clock tree synthesis stage. If you will not take care of your CTS stage, it will have a much skew in your design, and the tool will use lot of buffers to fix your hold violations. So conclusion is like you will have to take care of your design at every step, but mainly on the CTS as well as synthesis stage. You will have to take good care of your design in the I3C.
Thanks again to you for giving this interesting presentation, for us challenging work you've been doing, and thanks again to all the attendees. You have some contacts where you can either reach out. If you're already a MIPI member, you can reach out to the working group, to the I3C working group, or contact MIPI for membership. The I3C basic specification is freely downloadable, so you do not need to be a member. So thanks again to everybody attending, and
Thank you, everyone.
have a good day. And actually, for you, have a good evening.
Yes. Thanks, everyone.